Welcome back. This is Metaforming 2 Part 2. So, as I've mentioned in the previous slide, okay, so there are four basic bulk deformation process. There are rolling, forging, extrusion, and also wire and bar drawing. So, as for the rolling, the slab or place will be squeezed between the opposing roll in order to decrease the thickness of the work material. And then second one is forging, which is work is squeezed and shaped between two opposing dies. Okay, and the third one will be work is squeezed through a die opening, therefore it will take the shape of the opening. And the last one, wire and bar drawing, will be the reduction of the diameter of the wire or bar by pulling it through the die opening. Now let us look into the rolling process first. Okay, so the rolling process can be defined as the deformation process where you reduce the work thickness by the compressing forces exerted through two opposing rolls. For example, like in the picture below. So this one is the schematic diagram for the rolling process. If you can see, there are metal here, okay, and then it going through two roller, and then the thickness of the part will be reduced. So the rolls perform two functions during the process. One is it will pull the work into the gap between them through the friction, and then the second one, it will simultaneously squeeze the work in order to reduce the cross section. Now, type of rolling can be classified into two. One is based on the workpiece geometry, and second one based on the work temperature. In workpiece geometry type, there are two, which is flat rolling. This one is basically to reduce the thickness of the rectangular cross-section bar, and another one is shape rolling, where the square cross-section is formed into certain shape like I-beam, U-beam, or railway shape, railway bar shape. Okay, so for the work temperature, it is produced via hot rolling or cold rolling. Let us look into some of the product from the that produced through the rolling process. So for example, the starting material here is bloom. Okay, so it is square in shape, and once it's done, it will become a structural I-beam like this one, or it can also be produced into the railway rails. Okay, the second one is slab. Okay, so this rectangular slab can be reduced in terms of the thickness, and it will become a plate or sheet or coil like this one. And for this one, it is a billet, so it can be reduced into a certain bar and rod after the finishing process. So here is the diagram of the flat rolling. So this one is the roller. Okay, so for this roller there will be roll radius. Okay, and then in here also you will see the contact length, which is L, where the roller and the work material is in contact. Okay, so for the rolls there will be a roller speed, which is VR, and in the same time you will see the work material here with T naught is the initial thickness and TF is the final thickness, and there will be V naught, which is the initial velocity of the work material, and VF, which is the final velocity of the work part. Now let us look into some equation that we have to know in this rolling process. Okay, so the first one is draft, which is the amount of thickness reduction. So this one is represent as D. Okay, so D for draft equal to T naught minus TF, okay, which is the T naught is the initial thickness and TF is the final thickness. So that's when you will get the thickness reduction. And then reduction will be the draft expressed as the fraction of starting stock thickness, meaning that it will become R equal to D over T naught. If we put the equation here, it will become T naught minus TF over T naught. Then you will get the reduction ratio. So here are some facts that you have to know about the flat rolling. So the area where the plastic deformation of the work material happen is called the roll zone. Okay, so this area, the material will deform into the shape that we want. And then what we have to know is when the metal enter into the roll zone, the velocity of the starting material is slower compared to the velocity after it entered the roll zone. Okay, so this roll itself will move at constant speed. So based on this judgment, it is said that there will be one point in the process where the velocity v naught and v final will be the same. So at this area, uh, at this point when the velocity is the same, it is called no slip point. Okay, so for before this point, the roll will be moving faster than the material. After this point, the material itself will be moving faster than the roll. So here we look it into the diagram here for better understanding. If you can see here, so when the work material going inside here, the initial velocity will be lower compared to the one that coming out from here. So of course, because the work material is very thick, so in order for it to enter into the deformation zone, it will become slower. But as for this one, the thickness is already reduced, so it will move faster. Okay, so it is assumed that there will be one point in here in the L area where there will be no slip point, where the same velocity of the rolls, the velocity of the work material and the roll will be the same. Okay, and so that there will be no slip on this one. Okay, so here is the one that we have to know about the no slip point in metal rolling. Using the same concept and assumption, so the equation is given like because it is assumed that at this no slip point, the velocity will be the same. So it is calculated, they come up with the equation where T naught, W naught, L naught will be equal to T final, W final, and L final. Okay, so if L value is changed into in term of the velocity, you are going to get the equation T naught, W naught, V naught equal to T final, V final, and velocity final. So this one will be used, it's easier for us to determine the whether the thickness or the width final or the velocity final using this equation. Other than that, no slip point, or we call as the neutral point. Okay, so where the amount of slip between the roll and the work, this one we can measure using the forward slip. So the equation for the forward slip is given by S equal to V final minus V of the roller over the VR. So then you will get the forward slip equation. Based on this one also, we will be able to calculate the true strain. So the true strain, if you can remember from the previous example that I've mentioned, so the epsilon equal to ln T naught over the T final. So then you will be able to calculate the value for the true strain. Okay, so as for the average flow stress, you can still use the same equation, which is YF equal to K epsilon n over 1 plus n, and the draft also, the draft is the maximum thickness of draft can be done in one pass. Okay, so in here we can calculate it by using d max equal to a coefficient of friction squared and 10 times the roller radius. Okay, so it very dependent on the coefficient of friction and also the roll radius. So apart from that, the force that's supposed to be applied for the rolling on the roller also can be derived. Okay, so based on this one, F is force can be calculated by using average flow stress times the W and time the L. Okay, so we are going to see the value for the L, how the L is calculated. So as we already seen in the diagram before, L is the contact length. So the contact length is calculated by R in bracket T naught minus TF and then square root. So you will get the value for the L. And then we also can calculate the torque by using the T equal to 0.5 FL. F is the force, L is the length of the contact length. And then we can also calculate the power, okay, in order for us to perform the rolling process. So this one is calculated by using P equal to 2 pi NFL. Okay, 2 pi N, N is the rotational speed, F is the force, rolling force, and L is the contact length. Then you'll get the value for the power. So if we want to see the graph for the pressure in between the contact length, okay, so if you can see here, the pressure will start to increase until no slip point, that one where the peak of the pressure, and then it will start to decrease once it goes the no slip point. So this one all happen in the contact length area. The next point is shape rolling. Okay, so shape rolling is a work is deformed into certain contour cross section rather than the flat or rectangular shape only. So this one is accomplished by passing the work through roll that have reverse of the desired shape. So meaning that the roller is shaped into the inverse of the shape that you want to create. Okay, so the product usually created using this shape rolling are like I-beam, L-beam, U-channel, rail for railway track, and also round and square bar rods that I've shown in the previous slide. So here is the rolling mill for the hot flat rolling process. If you can see, the setup for the rolling process is very big and very hot. If you can compare the machine to the operator, which is just like a small person over here with a very gigantic process machine to perform the process. So due to that, the equipment is massive and very expensive. So in here, we are going to look into the rolling mills. So rolling mill configuration, there are 5 types of it. They have 2 high, which is only 2 opposing rolls, 3 high, where the work pass through rolls in both direction, meaning that they are stacking of 3 roller, and then we have 4 high where backing rolls support the smaller rolls, and cluster mill, multiple backing rolls on smaller rolls, and also tandem rolling mills where there will be sequence of 2 high mills. So here are the rolling mill configuration. Okay, so the figure here is, this one is for the 2 high, this one is too high. It is actually the work material going through here, and then it will go down here and on the configure the roller that is stacked together, 3 in like this one. We're going to see a video on this one so that you can see how the process take place. And then we have 4 high. So as 4 high, we have 2 big roller which support the 2 small roller here. Now here we see the cluster mill. You can see that there are 4 big roller which will support the small roller over here, and we also have tandem rolling mill. This one is for a continuous process, where if you can see, there are the stack of 2 roller here. Okay, the roller, but it is continuous, meaning that the material will go from one and then go directly. So if you can see here, the thickness in between here will start to reduce from this one to another roller. Okay, let us look into some problem. Okay, so a 30 mm thick plate made of low carbon steel is to be reduced to 25 mm in one pass. Okay, so it's already given, the D is equal to 25 mm in one pass. Okay, so in a rolling operation, as the thickness is reduced, the plate widened by 4%. yield strength of the steel equal to 175 MPa, and tensile strength equal to 290 MPa. The entrance speed of the plate is 77 meter per minute, roll radius 300 mm, rotational speed 45 revolution per minute. What they want is determine the minimum required coefficient of friction that would make this rolling operation possible, and B is exit velocity of the plate, and C is forward slip. Okay, now let us see some how this question can be solved. Now, it's already stated that for A, they want how much is the coefficient of friction, okay, the maximum coefficient of friction. So the only equation that we can use to calculate the coefficient of friction will be D max equal to coefficient of friction itself square times the R, right? So it's already given the D value, which is 30 minus 25, which is 5 mm. Right, so this one will be reduced in one draft, okay, one rolling process. So based on this one, we can calculate the coefficient of friction. Okay, so then the final value will be 0.129. Okay, the B question is they want it's given that the plate widened by 4%. However, it is not given the width of the work material, right? So for this one, they want the final velocity, right? So the equation that we can use is the T naught W naught V naught equal to T final um, W final V final. Okay. So as for this one, since the plate is widened by 4%, meaning that we can assume that WF will become 1.04, meaning that 100 plus the 4%, then you'll get 1.04 uh, uh, with initial. So when we put this value inside the equation here, you will get the since W naught you can take out, and then you will get the VF. Okay, so when you put it together, you will get the value 88.85 meter per minute. And then the last one, they want you to calculate the forward slip, right? So this one you have to calculate the VR first, which is 2 pi rn. Then you will get the speed, the velocity is 84.82 meter per minute. And then when you put it inside the equation here, which is VF minus VR over VR, you will get the forward slip is 0.0475. So the next question is a series of cold rolling operations are to be used to reduce the thickness of metal plate from 50 to 20 mm in reversing to high mill. So roll diameter equal to 600 mm, coefficient of friction of the roll equal to 0.15. Specification is that the draft is to be equal on each pass. So first, you determine the minimum number of passes required, and B will be draft for each pass. So when we are given this question, when minimum number of passes, how many times that we want to perform the draft to perform the rolling process, first you have to calculate what will be the maximum draft that you can achieve in one pass. Okay, so in here, so you can use the equation D max equal to coefficient of friction squared times the roller diameter. So based on this one, when you put the coefficient of friction is 0.15 times the radius for this one for the roller. Okay, so meaning 300, so it will become 6.75 mm. Okay, so it says that minimum number of passes. Here we have to see how much is the reduction that we want to make, which is 50 minus 20, right? So meaning that we have to reduce to 30 mm. So you have to give T node minus the T final, 50 minus 20 over the maximum, how many draft that you can create here. So it will become 4.44, of course, because the specification is given here is it has to be equal on each pass. Okay, then you can round it into 5 passes, but the meaning that the draft you can lower it from the 6.75. Okay, so then it will be 5 passes. So then what is a draft for each pass will be it will be then 50 minus 20 divided by 5, so it will become 6 mm. So here are some videos link, so you can look into the videos for better understanding of the rolling process. So that's the end of class today. Thank you very much. Assalamualaikum.